When you load batteries into a common flashlight, you are physically stacking them to increase the electromotive force, or EMF. Think of EMF as the total push provided by a power source that moves electric charges through a circuit. In schematics, this series connection shows a 6-volt and 8-volt battery in the same line. The 8 volts negative terminal connects directly to the 6 volts positive. This head-to-tail alignment shares the same polarity. Pushing together, we add their values for a 14-volt total EMF. Checking this terminal alignment is the first step in any circuit analysis. The direction of the push determines the basic math you need to perform. However, circuit behavior changes significantly if the sources are not pushing in the same direction. Here, the 6-volt and 8-volt batteries are in series, but their positive terminals meet in the center. In an opposing polarity connection, they push against each other. We subtract the weaker 6-volt push from the stronger 8-volt push, leaving a total EMF of 2 volts. Visualizing the direction of the current flow based on terminal symbols prevents common errors. Without checking the polarity lines, the math will not reflect the physical reality of the circuit. Let's test a longer chain with 3 cells, 5, 11, and 4 volts. Pause here to identify their polarities and calculate the total EMF. Since each cell is consistently connected negative to positive, we add the 3 values together for a total of 20 volts. This additive rule applies to any number of sources, provided the head-to-tail polarity remains unbroken throughout the entire series. The final configuration to consider is the parallel layout. This example shows 2 parallel branches, each containing a series of 4 2.0-volt cells. First, calculate the total voltage for just the top branch. Using our series rule, these 4 2-volt cells combine to provide 8 volts of push along the top line. The bottom branch is identical. Its 4 cells also add up to a branch total of 8 volts. A common mistake is to add these 2 branch totals together and assume the circuit has 16 volts. But in a parallel circuit, the branches are not stacked on top of one another's force. Because both branches connect the same 2 points in the circuit, they provide identical pressure rather than cumulative pressure. Think of it like 2 identical pumps side by side. They move more volume, but the pressure doesn't double. Therefore, the total EMF remains exactly 8 volts. To recap, add for same polarity series, subtract for opposing polarity series, and for identical parallel branches, the total EMF is simply the value of a single branch. These 3 patterns provide the foundation for identifying the total voltage available in a DC power source before you begin more advanced circuit calculations.